This unit is all about bonds. But no, I'm not talking about these guys. I'm talking about bonds. Chemical bonds. Chemical bonds relate to physical properties, specifically boiling point, melting point, hardness, and conductivity, both electrical and thermal. Also, magnetism. Different types of bonds will give us solubility or give us the properties of different solutions. We can also talk about bonds in terms of their strength, which derives from their bond energy, which is the energy required to break a bond, because breaking a bond requires energy. And just as there were many different types of James bond, there are many types of bonds, chemical bonds. So let's go over a couple of them. If you look at a compound like sodium chloride, one which contains a metal and a nonmetal, when sodium chloride, or table salt, is put into solution, into water, it dissociates, and the solution conducts electricity. This leads us to believe that there must be something in sodium chloride, because water by itself does not conduct electricity. There must be something in sodium chloride that conducts electricity. So we can say that there must be some sort of ions involved. Why does this happen? Well, it's because, in general, systems tend to the lowest possible energy they can conform to. They will try to go the lowest possible energy level they can reach. Just like students will try to take the easiest course they can, put out the least amount of energy they can. It's the reason that all my general kids want to take not AP chemistry, because they're lazy, because they conform to their lowest energy level. Atoms are the same way. Systems tend to the lowest energy level possible. When sodium and chlorine react, they form sodium and chloride ions, because electrons are transferred from sodium to chlorine, making it chloride. The attraction for a positive and a negative atom or ion is extremely strong, and separate they have far more energy than they do when they are together. I don't want to show them overlapping because they're not sharing anything. They are simply conforming to their lowest energy setting, which is together. This bond that forms between two oppositely charged ions is called an ionic bond. Ionic bonds have extremely high boiling points and melting points, and they're particularly hard. For example, sodium chloride or salt has a boiling point of 800 degrees Celsius. Sorry, a melting point of 800 degrees Celsius. Its boiling point is really high. And it's because the electrostatic attraction between these two ions allows them to be extremely closely packed to one another. And this causes them to be very thermodynamically stable. Ionic compounds typically form when an atom that loses electrons relatively easily reacts with an atom that has a high affinity for electrons. So an atom that loses electrons relatively easily would be a metal, and an atom that gains electrons or has a high affinity for electrons would be a nonmetal. So ionic compounds typically form between metals and nonmetals. The energy of interaction between a pair of ions can be calculated using Coulomb's law. See, that was a pun on the whole Bond thing. Q is the guy that gave Bond all his stuff, like Coulomb's law. Calculate the energy. Shut up, it's funny. Where the energy of the bond is derived from a constant times the charge of the first ion times the charge of the second divided by the radius, or the distance in nanometers between the ion center. So for example, sodium chloride, the distance between the centers of the sodium and the chloride ions is 2.76 angstroms. Or, if you were to convert that into nanometers, an angstrom is a tenth of a nanometer, so 0.276 nanometers. So we can go ahead and plug that into our formula, where R is 0.276 nanometers. The charge of the first ion is 1 positive. Charge of the second ion is 1 minus. So plus 1 minus 1 times each other is a minus 1. Minus 1 over 0.276 is negative 3.6. Negative 3.6 times 2.3 times 10 to the negative 19 is negative 8.34 times 10 to the negative 19 joules. That negative value indicates that it's an attractive force. Therefore, the ion pair has lower energy than the separate ions. If Coulomb's law comes out to be a positive value, then you have a repulsive force. So E would have a positive sign, meaning that the two ions would repel one another. So if you had a negative and a negative, that would be a positive 1 over, and I would have a positive value for Coulomb's law, and therefore two positively charged ions are going to repel one another. But hopefully by now you know that not everything exists between a metal and a nonmetal. Not all compounds exist as a metal and a nonmetal. So what happens when you have something that is both nonmetal? So something like, let's say, hydrogen. Hydrogen is just a proton with 1 electron. And if two hydrogens are brought together, you're going to have some very positive energy terms. I mean, a lot of repulsion, both between protons and protons. When you try to put two protons next to each other, and they're not going to want to do that. The two electrons are not going to want to sit next to one another. The only real attractive term between a hydrogen atom and another hydrogen atom is between the proton of one and the electron of another. What conditions could possibly favor this bond formation? Well, once again, it lies in the tendency in nature for any system to achieve its lowest possible energy. A bond will form if the system can lower its total energy. When you put two hydrogen atoms right next to one another, the energy between them spikes astronomically high, because the closer they get to one another, the closer the two protons get to one another, the closer two electrons come to overlapping in their orbitals, the higher the energy they have. Inversely, if you separate them by an infinite amount of distance, the energy between them is going to be almost negligible, because distance makes the attractive and repulsive forces begin to dissipate. The hydrogen atoms will actually position themselves so that the system can achieve the lowest possible energy. So the system will act to minimize the sum of the repulsive forces, the positive, and the attractive forces, the negative. The distance where this energy is minimal is called the bond length, which we can see according to this graph is 0.074 nanometers. This is the distance at which one hydrogen nucleus is attracting both electrons equally to the other hydrogen nucleus. And the positive repulsion forces, the positive energy value from Coulomb's law, is being offset by the negative attraction, the negative energy value from Coulomb's law, from the attraction of a proton for an electron. So electrons reside primarily, or they are found mostly, in the space between the two nuclei, where they can be attracted simultaneously by both protons. The potential energy of those electrons is much lower in this place because of the increased attractive forces in that area. You can also think of this in terms of force. The attraction of a proton for an electron is going to pull that proton closer to the other proton, and it will balance the proton-proton and electron-electron repulsion. And that distance of balance, where that balance occurs, is the bond length. When we encounter this type of bond where electrons are shared by two nuclei, we form a covalent bond. With ionic bonds, we showed an ion next to another ion and simply wrote them together, because that was the simplest ratio of these multiple ions coming together. In a covalent bond, these are individual bonds formed between individual molecules, and therefore we have a different way of showing them. You can show them as sharing two electrons, drawing the electron pair that they're sharing between them, or you can show it as a line if you're doing a Lewis structure. Either way is fine. The attraction between the two, the repulsion between the two nuclei, and the attraction between a nuclei and the valence electrons of another atom are the intramolecular forces. So it's the attraction between the nuclei and the electrons of a bonded atom, of bonded atoms. Intermolecular forces are the subject of our next unit, so we will not be talking about them very much in this unit, but they're the attractive forces or repulsive forces between whole molecules. So between one sodium chloride and another sodium chloride, or between hydrogen and another hydrogen molecule. Okay? Okay. When a covalent bond forms, the electrons that are being shared are going to have to develop a new bond orbital, which hopefully you remember from the previous unit was simply the motion of two electrons with opposite spin. So when a covalent bond forms, it disturbs the usual wave function or shape of the atom. Shape in loose terms. When you describe it on the APT exam, you should discuss it as the wave function. And this new wave function comes from these two bonded atoms and looks a lot like the original. However, the bond orbital is now concentrated in the region between the two nuclei. The electrons in the bond are concentrated between the two nuclei. Those electrons in that bond have a lower energy than the valence, so then when they were just valence electrons around one nucleus, because now two nuclei are keeping close tabs, quote unquote, on those electrons. And if there are lone pairs, if there are electrons that are not being used in a bond, they will develop their own wave functions away from the bonded region, where now electrons are more concentrated, they are being repelled by that region, and so any lone pairs, any electrons that are not utilized in a covalent bond will move away and develop a different wave function. So in an ionic bond, the bond orbital is strongest or is largest around the anion, because it now has more electrons. Whereas in a covalent bond, the bond orbital is more or less evenly distributed and electrons are shared by the two nuclei. Now, how well they share determines on whether or not something is polar or nonpolar, which is our next video.